Hello and welcome back to part 2 of the lecture on chapter 11 in the textbook Elementary and Middle School Mathematics Teaching Developmentally 10th edition. This is Dr. Brooks and this is for EDCI 349. So we've already talked about the first half of chapter 11. We are now on page 252 or 251, I'm sorry, and we are talking about development of invented strategies. Hey, listen, students don't usually invent strategies. We as teachers have to help them to be able to invent strategies. And the way that we do that is, if you refer back to chapter 9, we help them move through those 3 phases of problem solving. First, they're going to count on, then they are going to move to reasoning strategies. And when we give them those, I think we talked about 7 or 8 different types of reasoning strategies. When we show them and help them be comfortable with the reasoning strategies and they're able to move to mastery, once they're sitting in that mastery phase, that's when they'll be able to come up with their invented strategies, because they'll want to solve problems faster, more efficiently. Some of them might just like the challenge of being able to attack these problems in different ways. But we have to make sure that we provide a supportive environment where we allow the students time and we push them. Give them a little push. We allow them time to use those strategies. We provide programs that support the strategies. We ourselves support the strategies. We understand that there's not just one right way to solve a problem, and we want to make sure that we provide a supportive environment so that they can solve the problems. We want a model to support inventive strategies. There are 4 common types of inventive strategies to solve addition and subtraction, and that means basically that we're allowing students to invent a strategy, but chances are when it comes to addition and subtraction, they're going to come up with one of these 4. They're either going to break it apart, split it, jumpstart, or shortcut. So break apart strategy for a problem such as 146 plus 312 uses students' understanding of place value to start with the first number. So they're going to start. So if they have 146 plus 321, they are going to add 100 to 300. Then they are going to add 40 to 20. Then they are going to add 6 to 1. This is a problem that you would have thought you couldn't do mentally. But if you look at it, breaking it apart like this, starting left instead of right, we can do mentally. 467 can be done mentally. See, there's something to that. The break apart strategy emphasizes decomposing place value. So what we did is we just decomposed this. When we wrote it down, we composed it. We put them ones, tens, hundreds, and then we decomposed it. We broke it down hundreds, tens, ones. The jump strategy, let's put jump start. The jump strategy, not jump start, uses an empty number line, also known as an open number line, and then the students jump. So they start with a number line. They start here. We want to know what is, let's do 3 plus 3. So we're starting at 3, and then we're going to jump 1, 2, 3 to 6. Jump start. It uses an empty number line. Students might draw that number line when they're inventing this strategy. They might do it mentally. You might provide the number line for them. The shortcut method. Bar diagrams can also be effectively used to support students' thinking and help them explain their ideas to others. Bar diagrams work particularly well for students for contexts that fit a comparison situation. The shortcut strategy involves the flexible adjustment of numbers. For example, just as students use 10 as an anchor in learning their facts, They can move from numbers such as 39, 38 or 69 to the nearest 10. Then take the 2 or 1 off to compensate later. As another example, 51 minus 37 can be thought of as 37 plus 10 equals 47, and 47 plus 4 more is 51. Alternatively, the same problem, 51 minus 37, can be thought of as 51 plus 6 to get 57, and 57 minus 37 equals 20. Then subtract 6 and you get 14. In each case, the numbers in the problem and the type of problem will influence the strategies students use. Therefore, it is important to think carefully about the type of story problem you pose as well as the numbers you select so you can provide that supporting environment for the students to be able to pick different strategies by using different problems and different digits and numbers in the problems. And that way it can help more for a natural inclination to use whichever strategy you'd like to focus on today. Developing an inventive strategy for adding and subtracting single digit numbers or finding the difference between two reasonably close numbers. Many students will use counting to solve the problem. One goal should be to extend students' knowledge of basic facts and the 10 structure of number system so that counting is not required. We don't want students counting on. Spend some time looking at page 255, where it talks about adding single digit numbers and the challenges and why it's important to do inventive strategies. Remember, when a student counts on, they have increased likelihood of creating an error. Adding multiple digit numbers. The development of fluency with multiple digit addition and subtraction begins in grade 1. The addition of multiples of 10 and continues through grade 4, when students are expected to fluently add and subtract multi-digit whole numbers using a standard algorithm. This fluency must be built with years of exploration using concrete models or drawings and strategies based the inverse relationship between addition, subtraction, place value, and the properties of operation. Although double-digit addition is a focus of second grade, students in grades 3 and 4 may still be challenged by these computations. Problems involving the sum of two-digit two-digit numbers will usually elicit a wide variety of invented strategies, and it is those strategies that are the foundation for adding three-digit numbers and beyond. Some strategies will involve starting with one or other number and working from that point, either by adding to it or building tens or adding ones. Page 256. Subtraction as thinking on page 258. Students who know the think addition strategy for their basic facts also use the same concept for solving problems with multi-digit numbers. This strategy is amazingly powerful way to subtract and is particularly successful with students with disabilities. For example, 38 minus 19. The idea is to think. So let's come over here. This is an interesting setup I've got here. All right. 38. So we're doing think addition. 38 minus 19. The idea is to think, how much do I add to 19 to get 38? Notice that this strategy is probably not as efficient for 42 minus 6 with using join with change unknown problems or missing part problems. Will encourage the use of the think addition strategy. So join with change unknown or missing part. Here is an example of each. So here's an example of this. So your students might struggle with 38 minus 19. But what they can change it to, and what they might change it to, is what can I add to 19 to get 38? Well, if I add 1, I'm at 20. If I add 10, I'm at 30. And then if I add 8, I'm at 38. So what number is this? It's 19. So this might be easier, especially for your students with disabilities. This problem solved this way is easier for them to work than this problem, and they're going to be more efficient and get the correct answer more, so they'll be more fluent. Takeaway subtraction. Using a takeaway action is considerably more difficult to do mentally. However, takeaway strategies are common, probably because textbooks emphasize takeaway as the meaning of subtraction, even though there are other meanings. It doesn't always mean that you took something away. It could mean that something is gone. It can still be there. You just don't have access to it. See, that's another bad thing about takeaway. For example, I have my desk. There are areas of my desk that can't be used. So they weren't taken away, but they are subtracted because I don't have use of them. Same thing with this paper. When we're talking about area, there are parts of this paper I don't have use of, but it wasn't taken away. I just don't have use of it. If you lock a door in your house, is that room taken away? No, it's still there. You just don't have use of it. And so when we say takeaway, it can be misleading, especially in problems where you're not taking anything away. So these are all steps that you have to work through. Hey, listen. There are going to be some challenges, and you're going to need to extend in order to help students to do inventive strategies and to talk through how they solve problems. Why did they use that strategy? What if they don't know how to begin? How do they pick a strategy? If you have a student who walks in and instantly wants to start doing an algorithm, how do I handle that algorithm? Each of the examples in the preceding section involved sums less than 100, and all involved crossing a 10. Crossing a 10 is how we talked about building 10, and that can be a problem. Same thing with large numbers. Second grade students should add and subtract 3-digit numbers using a variety of strategies. How would you do these problems without using a standard algorithm? So if you have this problem, 487 plus 235 plus 623. How would you do that problem without an algorithm? You'd have to provide support, time, patience. Those are the three main: support, time, and patience. And we are getting Okay, so we're at while we're doing this real quick, just let me take 1 second to talk about because I'm getting text messages uh, about the quiz. The quiz is just to help you focus on the lecture. So one of the bad things, if you're like me, you opted not to go to an online school because you don't like online. I opted to work at a brick and mortar university because I like the face-to-face interactions. If you haven't noticed, I'm a people person. So when you put me in an online environment, I get distracted. I'm at home, so I have home life going on. I've got kids here, I've got grandkids here, I've got a dog here, I've got issues going on in the house. And so it can distract me from my online instruction. But if you tell me that there's a quiz that I have to pass, it gives me a purpose to focus on the quiz, on the content. So these quizzes will be brief. They will be pulled from the lecture, and they are here to help you focus. They will not be anything lengthy. There will be maybe 5 questions per chapter. Somebody was asking, is it going to be like the last test? The last test was 30 questions. It's not going to be anything that lengthy. Am I going to provide a study guide? Yes. This lecture is your study guide. Watch it, rewatch it, rewind it, and watch it again so that you know what is to be expected of you. All right, we're on page 261. Standard algorithms for addition and subtraction. Also, let me say this. If you look at your syllabus, it says that you are to read these chapters before I have my lecture. And then that way, it can help you pay more attention and focus on the lecture because you kind of know what I'm talking about, or at least you know which neighborhood I'm in. So especially now that we've moved online, reading before the lecture is going to help you focus on the lecture. And that's another reason why I'm using the study guides, these sheets, versus just me talking to the camera, because this is going to help me focus if I were a student. So I'm teaching this online as if I were a student. And I also remember I do teach online already. A good bulk of my day is spent teaching online. And so it's helpful to have something to keep you focused. And these would be a good place for me to pull those quiz questions from. So continue to send your questions. Remember, I will go live at 12 to answer questions, and just so you can see my face and I can see your face, and just forgive whatever chaos goes on in the background. So anyway, standard algorithms for addition and subtraction. Students are not likely to invent standard algorithms. So you will need to introduce and explain them. After you've done inventive strategies, after you've helped them move through the 3 phases, then you're going to want to introduce the algorithms to them. Given that it is critical that you teach algorithms in a conceptual manner, help students understand the units of hundreds, tens, and ones as they work. Place value is key, especially once we move to values greater than 10. So if you haven't given the students a good foundation in place value, then when we move to values that are bigger than 10, numbers that extend past 1 digit, students are going to struggle. So you don't want to skip any part of that. And that's why this book is something that I would keep by my teaching desk, so that when problems arise, I know how to address those problems. The standard algorithm requires an understanding of regrouping, which is exchanging a 10 in one place value for a 1 to the left. The terms carrying and borrowing are obsolete and conceptually misleading. The word regrouping may initially have a little meaning to your students, so start with the term trade, because that is what you're doing. You're trading a $10 bill for 10 ones. You're trading a $100 bill for 10 tens. And when you think about it as trading, you know that that's gone. We now have a new beast. Whereas with regrouping and borrowing or carrying, we never understood that that beast that was called the 10 is now 10 ones. Or that beast that was called 100 is now 10 tens. So when you call it trading, you can understand that I now have something new. Two things to remember in teaching the standard algorithm for addition. 1. Be sure students continue to view it as one possible algorithm that is a good choice in some situations, just as inventive strategies are good choices in some situations. And 2, as with any procedure or algorithm, it may begin with the concrete, then explicit connections must be made between the concept and the procedure. So you have to spend time actually trading. I taught a lesson to second grade where we just spent the whole lesson trading a 10 for 10 ones. And they were bankers and customers. They spent the whole lesson just trading and recording their trades and talking about their trades. Begin with models only, and then make sure that they have a written record of what they're modeling. So I told you just now about the customer and the bank. I use that one because that's the one that the students, you want something that's relevant. And most of them, if they don't go to the store, they want to go to the store. They've seen the store. That's a transaction that they can handle. And those are denominations that they know. They know a dollar bill. They know a $10 bill. They know a $100 bill. They know a dime. And they know pennies. And so you want to model first, and then you want to make sure that they develop a written record. And through this written record is where you can introduce the algorithm. Standard algorithm for subtraction. So this is for addition. So for addition, you model. For subtraction, you model. For addition, you want them to develop that written record. For subtraction, we want them to develop the written record, but we also want to anticipate the difficulty of zero. That concept of zero. So last night while I was doing my thinking on my lecture, and I thought about how students struggle with that concept of zero. I thought about this. You could give each student 2 packs of gum with 0 sticks inside of each pack. You could give them, let's see what I have here. I have a lot because I'm in my home office, so I have a lot of access to. So I could give them, here we go. Oh, 4 vehicles with 0 people in each vehicle. Four cars enter a garage. None of the cars leave the garage. How many cars are in the garage? See, here goes a situation where, did I take anything away? No. I just don't have access to it, or I have something that is unchanged. You want to anticipate, know this. Some of your students, if not all of them, are going to struggle with this concept of zero. We don't count it. We rarely say it. But when we put it in a number, it changes the value of the number. What do you mean? Here's 10. How many of you would like this much money? Versus how many of you would like this much money? Versus how many of you would like this much money? Versus how many people would like this much money? Zero is powerful. So let's not gloss over zero. Let's spend some time with zero. But I thought about that last night. I thought about the gum, but you could use anything. You could use boxes. You could use your Girl Scout cookie boxes. That might make them cry. With no cookies in each box. How many cookies do we have? Just anticipate. And then again, you want to develop a written record because that's where your algorithm is coming from. Trying to keep these lectures under an hour. All right, page 265, Introduction of Computational Estimation. Computational estimation is a higher level thinking skill that involves students in the decisions they need opportunities to think about and discuss. So, I have to present them with a problem, and then I have to allow them the time to think about it, discuss it, and try to solve it. So besides knowing how to reach exact solutions to problems, everyone needs to solve numerical situations that need an about answer. You have likely been in a circumstance where a friend has quickly done some approximate calculation in her head, and you realize how useful and important mental math skills are. I'm that friend. What's the tip? What's the answer to this problem? How much will we have to divide this bill into? Good at estimating. Common Core says that the goal of computational estimation is to be able to be flexible and quickly produce an appropriate and approximate result that will work for the situation and is reasonable. Mathematical Practice 5 for Common Core states that students should detect possible errors by strategically using estimation and other mathematical knowledge. Good estimators tend to employ a variety of computational strategies they have developed over time. So, understanding computational estimation. The goal of computational estimation is to be able to be flexible and to quickly produce a reasonable estimate. This is hard so we spend a whole lot of time wanting students to come up with the right answer, and then bam, we come to estimation, and now we don't want an exact answer, we want an approximate answer. This is an area where students struggle. They struggle because you've been telling me for 3 years or 4 years or a whole semester or 2 semesters or 9 weeks to give you the answer. Now you don't want an answer. Now you want an estimate of an answer. When I was a student, this was something that I struggle with. There are 3 different ideas when it comes to estimation. So we have measurement, estimate the length; quantity, estimate the amount; and then computation, give me an estimate of the answer. Some suggestion for teaching computational estimation. Use real life strategies and examples. The jar full of bears. Let's estimate how many bears are in here, little Teddy Graham bears. And let's estimate that based on some type of reasoning and strategy. Use estimation language. Words and phrases such as about, close, just about, a little more, less than, between are part of the language of estimation. Students should understand that they are trying to get as close as possible using efficient methods, but there is no one correct or winning estimate. So we just want them to get approximate, want them to get close, want them to get just about. Use context. Situations play a role in estimation. For example, it's important to know whether it's going to cost $950 to fix your car or $9,500 to fix your car. Could attendance at the school play be 300 people, 330 people, or 3,000 people? Simple computations can provide the important digits with knowledge of context, providing the rest. So we talked about estimating in this class. How many people in this class are at home right now? 20, 200, or 2,000? Well, for this video, 200. 20. For the school, it's 20,000. Everybody's home, hopefully. Accept a range of estimates. Offer a range as an option. Hey, listen, there is no one right answer. This is hard when you're estimating. There is no one right answer. 99 can be close to 90, and it can be close to 100. Accept a range. It can be close to 95 and close to 100. It can be close to 90 or 95. And lastly, focus on a method, not an answer. Remember that having students reflect on the strategies used by classmates will lead to additional strategy development. So make sure that your math class is talking just as much as your reading class, your social studies class, and your science class. And when I mean talking productively about the work that they're doing. For some reason, the math class is the quietest class. The teacher talks, the students work, the teacher talks. Whereas in the reading class, there are conversations going on. Students are talking about what they read, and they're talking about why they think this is the answer. Same thing with in other classes, but not in the math class. So make sure that we focus on the method, not just on the answer. Trying to keep these under 30 minutes each. They load better on YouTube if they're not so long. Computational estimation strategies. There's 3 different strategies that you can use to help students when it comes to estimating in addition and subtraction. Front-end method. A front-end approach is reasonable for addition and subtraction when all or most of the numbers have the same number of digits. Front-end addition. So if I have a bunch of numbers that have the same number of digits, I can do front end where I'm adding to the front. I'm estimating. So I can say 50, 30, 10. My estimate is 90. Rounding, which is kind of what I just did. I can round each one of these. Oh, front end might be I just add 4, 3, 1, 4, 7, 8, 80. Estimate would be 50, 30, 10. And then I can combine numbers. Well, I can say, well, 46 and 32, they're kind of like 40 and 40, which is 80, and then I can add another 10, which is 90. Compatible numbers. I can add compatible numbers. Remember, I don't want an exact answer. I want an estimate. All right, and that brings us to page 270. Common challenges and misconceptions related to addition and subtraction computation. Number 1. You have a student who gives this as an answer. Students incorrectly record an algorithm for addition, but not regrouping, and they ignore place value. How to help? Look on page 270, and this is number 1. How can you help students who have who incorrectly record the algorithm, or they don't know place value? How can you help them? When students add this is reverse regrouping. How can you help a student who has this problem? You can ask them to check their answers for reasonableness. Hey, listen, if I give you 50 cents and you already had 50 cents, how many cents you think you're going to have? You think you're going to have 16 cents? Don't say it with such an attitude like that. Confusing the multiplication algorithm with the addition algorithm. So that's what was done here. They multiplied instead of divide. Again, estimation would be good here. If I have 60 or 70, I have 70 cents. I'm going to keep going to money because I don't know, money's on my mind. I've got 70 rocks. My friend gives me 7 more rocks. How many rocks should I have? You subtract 2-digit numbers and this is what you come out with. The problem is when subtracting 2 multi-digit number, the student always subtracts the smaller digit from the larger digit. So for here, they were subtracting 0 from 3, and then they subtracted 2 from 5. You can start with a reminder about subtracting from 0. There's some other things that you can do to help. Look at page 271. We have regrouping issues. Students make mistakes when regrouping across zeros in a subtraction problem. How can you fix this? Look at page 271. This is a common one that you'll see. You will commonly see this one, and you'll see them all. So you'll see this. You'll see this sometimes when they're confusing their algorithm. This one too. And then the regrouping, when they subtract, a lot of times they'll subtract like this. Or when they add, they don't know place value. So 6 and 7 is 13. 5 and 9 is 14. Bam, there's my answer. 14, 13. So how can I help students who have a regrouping problem? Student overgeneralizes the equal addition or the same difference strategy in an addition situation. How do you help this? And then last, students think they have found an exact answer after they think they have to find an exact answer after they estimate. They're estimating. Don't make them find the exact answer. That defeats the purpose of an estimate. The estimate is just to find out, are we close? What do we need? How much do we need? We don't need to know exactly. We just need an estimate. On that note, that wraps up our lecture for Chapter 10. I want to thank you guys. The quiz will open up tomorrow, which is, who knows what day it is. All these days run together. It'll open up tomorrow and close Friday. Thank you.